feeling? Valid. And forgive my hiccups. Does anyone have any questions, etc., before we get started today? All right. Where was I? Today, we are going to be talking about friction. I said on Friday that lab this week would be about tension. I've since changed my mind. Lab this week is going to be about friction. Tension will be kind of present in the background, because really anytime there's rope, there is tension. So it was good that we talked about it when we did it, because there's going to be ropes in most labs going forward. But the main focus is actually going to be tension this week. And so today we're going to be talking about everything you're going to need to know about tension before you have lab this week. Now, friction is annoying as a physicist. As a person who exists on planet Earth, friction is both a blessing and a curse. It is a blessing because friction is the thing that keeps us from sliding around infinitely, which is good because that would get exhausting. It is a curse, however, because it prevents perpetual motion from being a thing we can have, and it is also contributing to the heat death of the universe, which is not great. To rewind a bit, though, and define friction in terms of the information you need, friction is a force that opposes motion. Whenever an object is trying to move across a surface, or even through whenever it's trying to move across a surface made of matter, or even trying to move through matter, friction springs into existence to try to stop that from happening. Friction opposes motion. And so, to use this image as an example, say we're trying to push this box, and we're going to apply a rightward pointing force. We want to push this box to the right. And the box does begin moving to the right. However, that box is sliding across the ground, and the ground secretly says, no, 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 no. And it applies friction to try to stop that from happening. So, surfaces create friction, and they create motion. That wasn't even a hiccup. I just said the wrong word. It threw me off. Surfaces create friction, and they create friction in such a way that opposes motion. So in this case, if we're trying to move the box to the right, the ground is going to say no and point with friction to the left. Whatever direction the motion points in, friction points opposite. That is true of objects sliding across the ground. It is frankly even true of you just moving your arm through the air, because air resistance is a type of friction. So whenever you do this and you physically feel the wind bristle your arm hairs, that is the air telling your arm, don't do that, and trying to stop your arm from moving through the air. Same is true in water, frankly. So between the two major fluids most humans are ever surrounded in, you can't really avoid it. Questions so far? Okay. Dang it. Every single surface does this. No matter how slick you think it is, no matter how recently it was oiled or polished, every surface creates this friction. Again, it means that if you push something and it does move, it will eventually come to a stop. That's why your car needs cruise control to not come to a stop on the freeway. And the question is, why does this happen? You guys know friction exists. You've dealt with it forever. But why does it happen? Do you guys have an answer for that?
Movement of an object affects the movement of the surface, which is inertia, so it doesn't really move.
That is part of it, because the object's inertia like if it's moving forward, the object wants to keep moving forward. So if friction didn't exist, objects would just continue on in straight lines, as if you were on roller skates all day. So without friction, everything would move in a straight line forever, and that's the effect you get in space, because space is as low friction environment as you can create, as long as you're not touching anything. And that's why things just fire off in straight lines through space forever until they start orbiting something. So the norm should actually be moving in a straight line forever, but instead, what we feel like the norm is, everything always slows down to a stop. And that's because friction is just everywhere. Every single surface creates it. And I'm going to explain to you why that happens, like where friction comes from. Because matter isn't just evil. It doesn't just say motion should never happen, because secretly matter wants to move if it's moving. That's what inertia means. The reason for friction occurs when you take a look at what's happening here and crank up the magnification. So here we have where the box touches the floor, and we are going to zoom in far beyond what the human eye can normally see. And we would get eventually at a certain, times a million magnification, you'd actually get an image that looks something like this. This is the jagged underside of our box, and this is the jagged top side of the ground. Now, from our macro scale human sensory experience, does the bottom of a cardboard box usually look like this? No, from our perspective, cardboard is fairly slick, fairly smooth to the touch. However, secretly, all solid matter is rough and jagged when you zoom in far enough. No matter how finely polished something might seem to be, it is secretly really bumpy when you zoom in far enough. And if you don't believe me, have you ever heard the phrase, matter is mostly empty space? That phrase is true, and it came about because all of the atoms inside of an object exist a certain distance apart from each other. So the atoms aren't touching, they're just kind of locked into a hover grid with each other. And that means that there's gaps between all of these atoms. And the top layer of atoms, if you extrapolate a little bit, is therefore kind of jagged. And so there's slots there where the top layer of atoms for something else can kind of slot in like saw teeth. Again, they don't ever actually touch. Atoms rarely ever physically interact with each other. But they get close enough where they form these patterns, and where two surfaces can lock into each other like gear teeth or saw teeth. The teeth on the bottom of the box lock into the valleys of the ground, and vice versa. The teeth of the ground lock into the valleys of the box. And this kind of locks the two objects in place. I would not recommend trying to slide two saws across each other, teeth by teeth, but it's not a fun experience. So once these two surfaces interlock like this, when you're trying to physically push the box sideways, you are literally trying to push saw teeth over it, past and through other saw teeth. And that's where friction comes from. You push this way, and the teeth push back against you. Every surface does this. Does not matter how polished or how recently it was waxed. Every surface is bumpy and jagged to some degree when you zoom in far enough. And that is why all surfaces create friction. And it is still a big old pain. That said, living in a completely frictionless universe would be also a pain for a different reason. It'd just be nice if we could turn it off, Turn it off inside of the working parts of your car. Turn it off when we need perpetual motion to exist. But no, it is just always on and always there. And because it is always there, anytime matter is trying to move past, over, or through other matter, you get this force of friction opposing motion. So that's where it comes from. And now we need to talk about how to calculate it. This down here is the formula for force of friction. I've turned it into the form you'll see on your formula sheet right here. Force of friction equals normal force times mu. These are the same things, I just write it weird. That is the Greek letter mu. If you're a Pokemon fan, I regret to inform you that it's spelled like this. It is a Greek letter. I believe it is functionally the Greek M, because uppercase mu looks just like an M. This is lowercase mu. And it means coefficient of friction. So it's one letter that represents an entire concept, like kind of like how lowercase g means acceleration of gravity. Mu means coefficient of friction. And I'll explain what that means shortly. I actually want to explain my normal forces here first. Force of friction equals normal force times mu. Normal force is here. Normal force affects friction because it determines how firmly these saw teeth lock into each other. Rewind. Why is this box touching the ground? Why does anything touch the surface it's sitting on planet Earth? Gravity. Gravity is pulling the box down, and it's been pulled to such a height that it is now intersecting with the surface of the planet. So gravity is pulling the box down, and for that reason, gravity is what is currently pulling the box physically into and against the surface. And therefore, likewise, the surface is going to push back. And the more the surface pushes back, the more these saw teeth wedge into each other. The greater the normal force is, the greater the force of friction. Notice if you doubled n and kept mu the same, force of friction would also double. Friction directly contributes to normal force because, reverse that. Normal force contributes directly to friction because it is a measurement of how firmly two objects are pressing into each other's surfaces. And the firmer that connection is, the harder it is to push these two sets of saw teeth past each other. That's why normal force is there. If normal force gets bigger, friction also directly gets bigger. And you have definitely noticed that before. Again, I try to take the math and apply it to the things you've actually witnessed. Have you ever noticed how, say it's moving day, the semester recently started, so I imagine some of you had to push a fridge into a corner. When you are pushing said heavy object, you're pushing, and maybe it's just not budging, it's just a very rough floor or something, or a really heavy fridge, and it's just not going. Have you ever noticed that sometimes, if you kind of lift up on the object slightly, not enough to actually pick it up, but just apply a little bit of upward force and then push, sometimes it'll go? When you're lifting it like that, again, you're not getting it off the floor, but you are reducing the normal force the floor exerts. The weight doesn't change, but the normal force does, because if you're kind of lifting it, the floor doesn't have to work as hard. And so if normal force drops, force of friction drops. And so lifting up on something slightly helps get it moving. The opposite of this would be if your jerk roommate decides to sit on whatever you are trying to push, and that's going to crank normal force up, and that's going to crank force of friction up. Does that sound consistent with what you observed? I hope not the jerk roommate part. So that's why normal force is there. It does actually play a role in friction. And again, pro tip, if something just isn't moving when you're pushing it, try lifting upwards on it slightly. Now, for the new thing, mu, the coefficient of friction. I'm likely just going to call it mu, because that's fewer syllables. but it stands for coefficient of friction, and I have a whole other slide for that. Hold please. There we go. Coefficient of friction represents basically how much friction a given surface interaction will create. Because normal force is not the only thing that factors in to friction, because this kind of ignores what types of objects are interacting. This only measures how firmly they are pressed into each other. This does not factor in, say, if one of them is highly polished, if one of them is socks on a bare floor, if one of them was recently greased or waxed, in the case of like machine parts. N doesn't factor that in at all, so we factor that in here instead. Mu represents basically how slick the interacting surfaces are. It is a coefficient of friction that represents how much friction a given interaction creates in comparison to other interactions. So it is a number that represents, again, basically how slick the interacting surfaces are. As a number, mu will always be a decimal value between 0 and 1. The reason for that is it is basically a ratio comparing normal force to friction. I'm going to rewrite the formula slightly. Force of friction over normal force equals mu. So same formula, I just sent the n from one side to the other. Written this way, mu's definition is a ratio of friction to normal force. And the more friction a certain amount of normal force creates, the higher the coefficient of friction is for that interaction. Now, mu will always be a decimal value between 0 and 1. It's always a tiny number between 0 and 1. If mu was 0 in this scenario, so if we had equals 0 here, that would imply that no friction was created by a certain amount of normal force between two surfaces. That would be if no friction existed at all, which again doesn't really happen. So you will never actually see a mu as low as 0. That is again like one of the holy grails of science. But it would mean in that weird hypothetical scenario that no matter how much normal force you applied, no friction would exist there. Now, scaling up from 0, very low mu's, again, they're never actually 0, but they can be very small. A very low mu, like 0.05 or 0.1, would represent very low friction, very slick surface. Very small amounts of friction in comparison to the normal force that generates it. So that would be like socks on a recently waxed tile floor or something like that. But the higher that mu gets, going from again like 0.1 up to 0.3 and so on and so forth until you reach number 1, you get more and more friction for however much normal force is applied. And so a mu of like 0.4 would represent most things against dirt surfaces. And a mu of 0.8 would probably be a surface that is just covered in dirt stains and hasn't been waxed in eons. All the way up to eventually a mu of 1, which would mean that in that scenario, all normal force generates directly into force of friction. It'd be a direct one-to-one correlation. So again, it's a ratio comparing normal friction to normal force. Low mu means less friction. High mu, high, it still tops out at 1, means more friction, as much friction as the surface can create. You will always be a decimal value between 0 and 1. And another weird quirk of it is that it is also unitless. Mu does not have a unit attached to it. And the reason for that is, again, this is the force of friction formula, just rearranged. Notice in this formula, we have force of friction divided by normal force. That is force over force, newtons over newtons. The unit just cancels out. And so as a result, mu will never have a unit. It's just a small decimal number by itself. It's like the only time that happens in here. It's also not a vector. I told you I'd point out if things are vectors or not. It's not a vector, doesn't have a unit, doesn't have a direction. Excuse me. Questions so far? All right. We're going to start doing some math to practice this. One thing I'll point out before that, though, there are infinitely many mu's because there are infinitely many different surface interactions. One mu represents how two different surfaces are interacting. So there's a mu for socks on tile. There is a mu for rubber-soled shoe on carpet. There is a mu for plastic against stone tabletop. There's a different mu for every pair of surfaces. And for that reason, there are infinitely many mu's, and you do not have to memorize any of them. Yes?
I guess that was going to be my question is, if we were given a question like using mu, would it be given to us?
Yes,
It's
either the
always-
question would tell you mu, or as I'm about to show, you'll be given everything you need to find it.
Okay, but we're never going to have to you're not going to be like,
Yeah, no, you do
Shoe
not have to
on
memorize,
carpet.
say, the mu of every different possible thing acting on greased metal or something
how
like
do
that.
they determine that?
How do they measure mu?
Yeah.
Well, to kind of give an example, the sample question I'm going to lead into involves pushing a box across the floor. They would physically exert forces on the box in order to see at what point the box starts moving, what acceleration the box has when that force is applied. They would figure out the force of friction and then use that to figure out what mu is. We don't have like a machine that can scan the floor and give you a list of mu's. It's, the only way to do it is trying just to calculate it. There isn't a table for it either, because again, there's infinitely many things, and it changes if the floor hasn't been washed recently. There's no real way to build a database for that. And for that reason, you do not have to memorize a single one of them. You'll either always be told mu, or as we'll demonstrate here, you'll be given the tools to find it, and that will be the point of the question. Does that answer the question?
Yes.
Okay. Any other questions, concerns, inquiries, etc. before a little bit of sample math? All right. We are going to push a 250 kilogram block horizontally across the ground. We need, collectively, all of the people trying to push this box, a lump sum of 1,000 newtons to even begin to make this box budge. To kind of set the frame of reference, this 1,000 newtons is the breaking point of friction. To, again, continue painting this physical picture here. We're exerting 1,000 newtons. The box isn't moving yet, but it's just about to. We can feel it's gonna budge. If we increase by just 1 more newton, it's gonna start moving. So this image is the breaking point. I want to set that up ahead of time. So we've all the people present have teamed up, pushing as hard as they can. We're at 1,000 newtons, and the box is about to move. We just need 1 more. We're examining the moment before it begins sliding. Okay, so far? All right. So, given that context, given that it's not actually sliding yet, we're hitting that friction breaking point. And since it's not sliding yet, I'll set up acceleration is 0. What would the value of the force of friction be in this scenario? 1,000. Very good. I'm going to demonstrate where the number comes from, just so you have it written down. First, though, looking at this picture, what direction is friction going to point? Leftward. Very good. If we're pushing to the right, if we want it to accelerate to the right, friction will always point opposite that, so here that'll be to the left. So our applied force is directly opposed by the force of friction. And if those are the only two x-axis forces, net force in the x-axis would be 1,000 plus force of friction, and if the box isn't accelerating yet, they must add up to 0. If those are the only two x-axis forces, they're likely equal and opposite, so in this moment, force of friction would be negative 1,000 newtons. Negative just meaning leftward. So, if something is not currently moving, like there are forces on it but it's not budging yet, that means that in that moment friction is currently having a tie with the forces that are trying to make it move. Here I have an eraser, and I am currently exerting force on it. It's a very little amount of force, and it's not enough to currently make it start moving. If I'm currently exerting about 1 Newton to the right, friction might be able to do a maximum of 1,000 newtons, but it only really activates in steps required. So say this thing could create 1,000 newtons of friction, but if I'm only exerting 1 Newton, it's only going to push back with 1 Newton. And it'll ramp up to 1,000 as I push harder and harder. So friction only activates as much as it needs to before it breaks and motion starts. So in this moment, we found that maximum, but if we were exerting less than 1,000, friction would in that moment be less up until we crank up to this maximum. So friction is not always going all or nothing. It ramps up to this as required. And we know this because if we take our hands off of the box and this 1,000 Newton force just vanishes, if friction was still pointing to the left, imbalanced, suddenly the box would take off to the left. But what actually happens is if we stop pushing, friction also vanishes because it only opposes either motion that is currently happening or motion that is trying to start. And if motion isn't trying to start, friction just turns off. So again, this maximum is only here when we are pushing on it, testing the limits of the friction. If we're pushing less hard, it's not actively at the maximum, and if we're not pushing at all, it just goes away. That makes sense? All right. Now, in this scenario, we've been testing it to find that maximum, and if we exert more than that maximum, it will break. If we exert 1,001 newtons, the net force is now 1 Newton to the right, and it starts accelerating. So this is the moment before that. So force of friction, we determine it's 1,000 newtons this way. And so the next question then is, what is the coefficient of friction that is creating this force of friction? What is the coefficient between specifically the surface of this box and the surface of the ground it is sitting upon? So we determined what force of friction is. We want mu. How do we proceed? All right, we are going to have to figure out normal force. That's because the only formula with mu in it is our new one. Force of friction equals N times mu. We figured out maximum force of friction. We want mu, so we need something to fill in for normal force here. What axis is normal force pointed in this case? The y. So we're going to have to also now analyze the y-axis like we just analyzed the x-axis. I answered my next question. It's going to point vertically upwards because the ground is pushing up. What other y-axis forces must be present? Very good. It's not a trick, I promise. Gravity's going to pull down. If those are the only two y-axis forces, then we can analyze them like we did the x-axis ones. So now I'm going to do net force y. Normal force up, force of gravity down. And what would the net force in the y-axis be if we're pushing this box sideways? 0. It's not accelerating up or down, therefore the net force vertically is 0. And so it's sitting on the ground. This is like logically we can arrive at the conclusion normal force of gravity would be equal and opposite in this specific scenario. How do we find force of gravity? Very good. So to fill in that formula, force of gravity is equal to mass times the acceleration of gravity. Therefore, normal force will be equal to, well, the variables. Mass at 250 kilograms. We don't have to convert anything. Times negative 9.8 equals 0. Therefore, what is the numerical value of normal force? (2,450 newtons up). And with that number, we can now come along to our new formula. Force of friction is 1,000 to the left. Normal force is 2,450 up. And now we can solve from here. Questions, opinions, concerns? All right. Now, as we work towards getting an actual number here, I'm going to point out a weird quirk about this formula. This formula is one of the only times where we're going to plug in intentionally an x-axis variable and a y-axis variable. This formula kind of bridges the two axes. It doesn't really, it's designed to do that. This formula is meant for this. It's just about the only time we're going to do that out of the gate. But because of that fact, because we're bridging axes here, something weird has the potential to happen in our answer here. Because we've defined left as negative and up as positive. So if we work this through traditionally, we're going to get a negative mu. And that's not really a thing. The reason this happens, the reason we're able to work around this, is because since this formula is bridging axes, again, we've got x here and y here. The quirk here is that one axis doesn't really care about positive or negative in the other. Y only cares about positive and negative up or down. It doesn't understand positive or negative backwards and forwards. Y has no understanding of x and vice versa. So the y-axis here doesn't really care that the force points left, because really the same thing would be happening if we just decided to push to the left and then friction would point to the right. Friction only exists to oppose motion. It doesn't really care about positive or negative. So this formula doesn't really care about positive or negative. For that reason, to just try to avoid this weird quirk, that marker's out of ink. Wow, I never hit the can. I recommend on your formula sheet adding absolute value brackets around normal force and friction. Just to mitigate, again, if one of the numbers gets plugged in negative, avoid the weirdness that is a negative mu. Because if I'm reading your work, I can understand where that came from, but if you put a negative mu in the WebAssign, it's going to have a headache. For that reason, the absolute value brackets will get rid of this negative before we do anything with it, and we'll get a positive mu, since mu, again, is just a unitless ratio that doesn't care about positive, negative, direction, etc. So, positive 1,000 over positive 2,450. I keep wanting to say that wrong. Equals mu. If my memory serves, that's about 0.41. Questions arriving at that number? What unit would we put on that answer? And that one was a trick. Mu doesn't have a unit, so you just kind of leave it as is. So the answer is just 0.41. Don't have to do anything to it. And that is a fairly average coefficient of friction for just a normal surface. Like probably a little bit slicker than gravel, but you know, it's consistent with what you'd expect. I guess Phil. All right. Now, for the twist. I skipped this part when I was reading over this slide. There are two types of friction, and therefore there are two different types of coefficients of friction. The two types are called static and kinetic. So static friction, and then separately kinetic friction. So there's two different types. And for that reason, there's technically two different friction formulas. One of them says force of friction static equals normal force times mu static. And the other one says force of friction kinetic equals normal force times mu kinetic. There's two different types. It's really just the same formula. It's just if you plug in a static mu, you get a static force of friction, and vice versa for kinetic. And I forgot the door was in the way. I will now explain why there are two types of friction. Cast your mind back to earlier when I was comparing what we were talking about to pushing a fridge across your floor. And I mentioned that, you know, lifting upwards can reduce the friction, and that's why you might want to do that, because normal force is tied to friction. When you're pushing that heavy object, have you ever noticed that it can be a pain in the butt to get it to budge? You're pushing and shoving and it's just not going, but eventually you get it to budge. Have you ever noticed that once it starts moving, it's easiest to keep it moving than to stop and start again? Because if it stops, you just have to push and push again to get it to budge. But once it's actively in motion, it's easier to act, like the same amount of force will keep you going, and you just don't want to stop until you're done. Does that sound familiar? Okay, a couple people are nodding. That is the difference between the two types. Static friction tries to hold the object in place and keep it from ever beginning to move. And static is the stronger of the two types. Kinetic is the type of friction you have if two things are actively in motion against each other. And kinetic is weaker than static. Remember earlier when I said friction exists because all surfaces are jagged when you zoom in far enough and the saw teeth jam into each other? The reason that static friction is greater than kinetic friction is because if two objects are not yet moving, their shark teeth like this are jammed into each other as far as they're going to go. And they do not want to budge, at least not if you're doing it like this. You can lift, but if you're pushing sideways, it's not a good time. So static is stronger than kinetic because the teeth are fully wedged into each other. Once you overpower static, once you exert enough friction to actually jar them loose and get them to start moving, as long as you keep them moving, you don't give them time to really sink into each other. You just got them grazing across the surfaces of the other one, or gliding, or possibly. And so as long as you keep it moving, they don't have time to sink in and get stuck again. So that's why the force of static friction is greater than the force of kinetic friction, and therefore the coefficient of static friction is greater than the coefficient of kinetic friction. So not only is it pointless to try to memorize mu's because there's infinitely many surfaces that interact, there's double infinitely many mu's because every surface interaction has one for static and one for kinetic. So again, you don't have to memorize any of them, but you may have to solve for 2 of them. And that's what lab will be about this week. The difference between them, how to find them, et cetera, et cetera. Questions so far? All right. So, with all that said, what type of friction were we working with in this example? Static. Very good, because the box wasn't moving yet. So to be as accurate as possible, I'm going to come back in and add little s's to all of my force of frictions and to all of my mu's. So the subscript s just tells you static versus kinetic. That does mean that force of friction static and force of friction kinetic each have 2 subscripts. And so now what I'm going to do, as the last thing of today, is add on to what we just did. Same setup, so the original details aren't changing, but I'm going to add that once we exert that 1,000 newtons or more, and then we officially break static friction, and we keep pushing with 1,000 newtons, the box now begins accelerating at a rate of 1 meter per second squared. Therefore, what are the values of kinetic and static friction? What are the coefficients of kinetic and static friction? We've already found the static ones. So now we're going to do the kinetic ones. So for kinetic friction, our x-axis has now changed because we're looking at a different, weaker type of friction, and the net force is no longer 0. So this is kind of a before and after scenario. This is the before, and now that friction is broken and the object has started moving, this is no longer true. So this is the before stage. The after stage, we're still applying 1,000 newtons. Now we're going to be opposed by a different amount of kinetic friction, and the net force is no longer going to be 0 because the net acceleration is no longer 0. Instead, net force equals mass times acceleration. So I'm going to put in 250 times 1. Mass of 250, accelerating at a rate of 1 meter per second squared. There should be a squared there, pardon me. It does say accelerate, but I need my units to be correct. There we go. So, this is going to change the value of the friction we are currently dealing with, but since we know the acceleration, we can just find that force. So there's nothing else we have to find to get there first. We know the mass times acceleration. It just isn't 0 anymore. So force of friction kinetic is going to be equal to 250, because the times 1 doesn't do anything. Bring the 1,000 over. Minus 1,000, force of friction kinetic is now going to be negative 750 newtons. It is weaker than the maximum that static is able to create. That is consistent with what I said earlier. The value for our force of kinetic friction is less than the value of our static friction. Same direction, they're both negative, meaning backwards, but different strengths. And that's why the same amount of force needed to budge the thing is now able to keep it moving, keep it accelerating even. If you wanted to move it at the same speed, you could use less force. Really, if you pushed it with just 750 newtons, you'd keep it moving at constant speed. Right now we're having constant acceleration by overpowering it. Questions so far? Okay. Well, with that found, we can use the kinetic version of the friction formula to just figure out what the kinetic mu is. So that would be absolute value of negative 750 equals absolute value of the same normal force, because the y-axis didn't change at all, times mu k. Mu k is going to be 750 over 2,450, so 0.3. Approximately 0.3. Notice that not only is the force of kinetic friction smaller, the coefficient of kinetic friction is smaller. How you guys feel? All right. That's everything I wanted to cover today. Whenever you have lab this week, make sure to bring these notes. Any questions before we break? All right. Have a great day. Think about types of friction when you encounter them, I guess. Maybe that's optional. And have a nice day.